told you that the 95% confidence intervals you rely on every single day in your clinical practice don't actually mean what you think they mean?
Right. It's a rather terrifying thought, isn't it?
It is. And what if, the p-values you're skimming in the abstracts of all those major psychiatric journals are, well, statistically speaking, answering a completely different question than the one you actually intended to ask?
It is a profoundly sobering reality. I mean, we like to imagine medical knowledge as this collection of hard, immutable facts. But much of what we consider truth in modern medicine is really just a highly structured mathematical approximation.
Exactly. Usually when we talk about a medical diagnosis, there's this expectation of sort of mechanical precision.
Right.
You break your arm, the x-ray shows a jagged white line, and the orthopedic surgeon just points at the film.
Yeah, broken or not broken, you can literally see it with your own eyes.
Right. But then you step into the world of psychiatry. You step into the clinic, and suddenly that x-ray machine is utterly useless. We're looking at a diagnostic landscape that is entirely murky, which I suppose brings us back to the anchor for all our discussions in this deep dive.
Spot on. Psychiatry is the study of how brain, mind, and experience interact, and how that process can go wrong.
And you cannot exactly put someone's experience under a microscope. You can't draw a straightforward blood test to identify a fractured mind.
No, you can't. Which leaves us navigating these incredibly muddy diagnostic waters. Because we deal with constructs that are inherently latent, hidden from direct view, we are forced to rely on proxies.
Right. Things like clinical observations, subjective patient reports, behavioral scales.
Exactly. And wherever there is human observation, there is profound uncertainty. There's noise. So the fundamental question becomes, how do we know if a new treatment actually works, or if your patient just happened to have a remarkably good week?
How do we separate the genuine signal of clinical efficacy from the deafening noise of human variation? And I think that brings us to the central metaphor of our deep dive today. We're exploring what we might call the architecture of truth.
The architecture of truth. I love that phrasing. It sounds quite philosophical, but we are genuinely talking about something intensely foundational here.
We are. We're drawing from the core concepts of statistics and experimental design, specifically structuring our conversation around the framework found in Kaplan and Stadok's comprehensive textbook of psychiatry.
And look, I know the mere mention of statistics and experimental design can immediately induce, a desire in many clinicians to skip straight to the conclusion of the paper.
Oh, absolutely. Just tell me what drug to prescribe.
Right. But these concepts, they're not just arcane mathematical hoops that researchers jump through just to get a publication. They are the structural spine. They are the methodological backbone preventing the house of clinical knowledge from just collapsing under the heavy weight of our own biases.
Without this architecture, truth in psychiatry isn't just elusive. It is dangerously subjective. Going all the way back to 1974, Jerry Cornfield, in his presidential address to the American Statistical Association, declared that statistics is the bedfellow of the sciences.
A brilliant quote. And yet, even today, you pick up a psychiatric journal and you're bombarded with this incredibly dense lexicon. Chi-square, analysis of variance, p-values.
It's a lingua franca that, let's be honest, many of us pretend to speak fluently, but deep down we're often just frantically looking for the translated summary at the end of the text.
Yeah, we've all been there. But simply reading the abstract or the discussion section of a psychiatric paper is akin to using a computer without any understanding of the operating system.
Right.
Yes, it works for a while, you can type your document, but you don't know why it's working, and more importantly, when it eventually crashes or produces an error, you have absolutely no idea how to fix it.
You're just staring at a blue screen.
Exactly. To independently judge the strength of clinical evidence, to really appraise whether a treatment should be given to the vulnerable patient sitting across from you, you must understand the methods. We cannot just blindly accept that peer reviewers did their jobs perfectly.
Which is the core mission for this deep dive. This isn't going to be a rote recitation of textbook formulas for you. We're aiming for a conceptual synthesis designed to build your mental models and, strengthen your clinical reasoning.
We'll trace the path from the foundational mechanics of probability all the way to the messy real-world reality of clinical trials and missing data.
So let's start at the very bottom of that architecture, the building blocks of uncertainty. Before we can test clinical realities, we have to understand how we quantify the unknown in the first place. Probability is a word we toss around casually, right? Like, what's the probability it'll rain?
Yeah, we use it colloquially all the time. But mathematically, specifically in the frequentist tradition, which dominates most of our literature, it means something very rigorous and specific.
Right, frequentism.
Yes. In the frequentist foundation, probability is defined strictly as the long-run relative frequency of an event occurring in infinite replications. It has nothing to do with a subjective feeling or a singular educated guess.
Okay, so if you throw a perfectly fair die, the probability of rolling a 6 is 1 in 6.
Right. And the reason is that if you rolled that exact die infinitely many times, the proportion of times it lands on a 6 will mathematically converge to exactly 1/6.
Infinite replications. I mean, I see a massive philosophical gap there right off the bat. In the clinic, I only have one patient sitting in front of me at a time. I'm not seeing infinite replications of a 45-year-old man with treatment-resistant depression.
No, you're not. And that gap, that's the central philosophical tension of medical statistics. We are applying long-run population rules to individual singular events. But to even begin that process, we have to define the universe of possible events for our experiment.
Which in statistical language is called the sample space, right?
Exactly. The set of all possible simple outcomes of a random experiment.
So, sticking with the die analogy, the sample space is simply the faces. 1, 2, 3, 4, 5, 6.
Precisely. But abstract concepts like faces of a die, or in our field, severity of a symptom, are quite difficult to manipulate mathematically.
Fair.
We need numbers. So this requires the concept of a random variable.
A random variable?
Yeah, it's essentially a mapping function. It takes the sample space and maps it onto the real number line, assigning a numerical value to each possible outcome. Let's say we're observing the roll of the die. The concept of the roll itself, the random variable, is usually denoted by an uppercase X.
Right.
But the actual specific observed outcome, once the die stops moving, is denoted by a lowercase x.
I see. So uppercase X is the abstract potential of the roll, and lowercase x equals 6 is the concrete reality that just happened on the table.
That's it.
And presumably every single outcome in that sample space has a probability assigned to it, and those probabilities have to add up to 1 because you are absolutely guaranteed to get one of the outcomes in the space.
Exactly. But that is the rule for discrete variables, where outcomes are distinct categories or whole numbers. You can't roll a 3.14 on a standard die.
True. But in psychiatry, we rarely measure things so neatly, do we?
Almost never. We are almost always measuring things that exist on a continuous spectrum. Think about the severity of depression on a Hamilton scale, or a patient's serum lithium levels, or their reaction times in a cognitive test.
Right. These aren't discrete buckets.
Not at all. Dealing with the spectrum requires a fundamental shift in how we think about probability, which leads us to probability density functions, or PDFs.
Okay, PDFs, not the file format.
No, definitely not the file format. For a discrete variable, you have a finite number of outcomes, and each gets a specific slice of the probability pie. But if the range of outcome values includes all possible values in a continuous interval, the maths changes completely. For a continuous random variable, the probability of observing any single exact mathematically precise value is technically 0.
Wait, let me stop you there because that sounds completely counterintuitive. If I take a blood draw and measure a patient's serum lithium level, the lab sends back an exact number. It has to be some number. How can the probability of that number be 0?
It's a great question. Think about the nature of a continuous line. There are infinitely many possible points on it. What is the probability that a patient's true underlying lithium level is exactly 0.800000000 ad infinitum down to the subatomic level?
Oh, I see. It's vanishingly small.
It's essentially 0. So instead of looking at single points, we have to look at intervals. We ask, what is the probability that the value falls within a certain range? We visualize a curve, the probability density function. The area under that curve within a specific interval gives us the probability.
I can picture that. It's like asking about the exact location of a raindrop hitting a puddle. The chance of it hitting one specific microscopic coordinate is 0, but the chance of it hitting within a 1-inch circle is measurable. We just measure the area.
That is a fantastic analogy. Yes.
So instead of asking, what is the probability the depression score is exactly 12.345, I ask, what is the probability the score falls between 12 and 13?
Exactly. And if you want to know the probability that a variable takes a value less than or equal to a specific number, you use a related tool.
Yeah.
The cumulative distribution function, or CDF.
Right, cumulative.
Yeah, you calculate the entire area under the PDF curve from minus infinity all the way up to your specific value. As you move towards positive infinity, that cumulative probability eventually reaches 1. Meaning you've covered every possible outcome.
Okay, so we have these distributions, these shapes that map out probabilities. When reading literature, the shape we encounter constantly is the normal distribution. Why is that particular shape so foundational?
The Gaussian distribution, or the normal distribution, is your classic bell curve. It belongs to what we call parametric forms. In parametric analyses, we assume we know the overarching architectural shape of the data's probability density function.
So the shape is fixed, but it has a few unknown dials we can turn, which we call parameters.
Precisely. The normal distribution is incredibly elegant because it's a translation parameter family.
Meaning you can slide it around.
Yes. The curve retains its exact symmetrical bell shape, but it slides left or right along the axis as you change its mean. The peak, which represents the mode, the mean, and the median, all occur at the exact same point.
That's convenient.
Very. The entire infinitely wide shape of a perfect normal distribution is dictated by just two dials. The mean, which dictates central tendency, and the variance, or standard deviation, which dictates the dispersion or spread of the data around that mean. If you know those two numbers, you have completely defined that theoretical universe.
But clinically, we never just measure one thing in a vacuum, right? A patient isn't just a lithium level. We need to understand how different events or symptoms relate to each other.
Which brings in conditional probability and independence. Let's look at two separate variables. We say two random variables are independent if knowing the outcome of one gives you absolutely zero information about the outcome of the other.
Think about the Clinical Global Impression Scale, the CGI, which we use constantly in trials to rate patient improvement. If I have a trial comparing a new antidepressant to a placebo, I'm looking at two variables. Variable 1 is the treatment assignment, drug or placebo. Variable 2 is the CGI improvement score.
Yeah.
If the drug is completely useless, those variables are independent. Knowing they took the drug tells me absolutely nothing about whether they improved.
Exactly. But if the drug actually works, those variables become dependent. The probability of seeing a patient rated as very much improved on the CGI scale, given that they received the active drug, should be quite different from the probability of seeing them very much improved, given that they received the placebo.
Ah, the given that.
Yes, that given that is the essence of conditional probability. It is the distribution of outcomes conditioned on a specific value of another variable. When we use tools like the chi-square statistic, we are fundamentally testing contingency tables to see if these row and column variables are truly independent or if they are conditionally linked.
And taking it a step further, when we track patients over time, we measure clusters of symptoms simultaneously. Sleep architecture, appetite, mood, psychomotor agitation.
That introduces multivariate random variables. To describe how multiple dependent variables move together, we calculate their covariance. It measures the average of the product of the differences between each outcome and its mean.
Okay.
But covariance is notoriously difficult to interpret intuitively because its value depends heavily on the specific scales of measurement used.
Right. If you measure sleep in hours versus minutes, the covariance number changes wildly, even though the biological reality hasn't changed at all.
Which is why we standardize it. We divide the covariance by the product of the standard deviations of the two variables. That mathematical normalization gives us the correlation.
Ah, correlation. The famous metric between -1 and one that measures the strength and direction of the linear relationship.
Spot.
I can already hear the collective sigh of 1,000 busy clinicians listening to this. This is beautiful theory. But why does a psychiatrist managing a chaotic inpatient ward need to think about sample spaces and multivariate distributions? Isn't this just academic navel-gazing for the lab?
It might feel that way, certainly. But if you look closer, this math is just the formalization of clinical intuition. Every single patient you evaluate is a multivariate data point drawn from a vast, unseen sample space.
Right.
When a patient presents with sudden psychomotor retardation, you are instinctively calculating conditional probabilities. What are the chances of observing this specific presentation given a history of bipolar disorder versus a major depressive episode? You're intuitively running a complex algorithm.
I see. And if I'm reading a paper claiming a new drug is a breakthrough, I need to know if the authors properly accounted for the covariance of the symptoms.
Absolutely. If a researcher treats a patient's improvement in sleep and improvement in mood as completely independent events, rather than highly correlated variables emerging from the same biological organism, their entire mathematical architecture is flawed. They are effectively double counting the benefit.
That bridges the theory to the practice perfectly. Okay, so we have our building blocks, probability, parameters, distributions. But here is the problem. In the real clinical world, we never actually get to see the true parameters of the universe. We don't have the luxury of infinite replications.
We certainly don't.
We only have the limited, noisy, messy data we managed to scrape together in our finite clinical trial. So how do we work backwards? How do we use a handful of data points to guess the hidden true parameters of human biology?
We use parameter estimation. And the premier conceptual approach to this was introduced over a century ago by Sir Ronald Fisher, maximum likelihood estimation, or MLE.
Maximum likelihood estimation. The name is somewhat self-explanatory, but walk me through the actual mechanics of it.
Think of it like a detective arriving at a crime scene. The true sequence of events, the parameter of the universe, is unknown. But the detective has observed a specific set of clues, the data.
Right.
The likelihood is a mathematical measure of how likely it is to have observed this exact specific set of clues, assuming a particular sequence of events took place. Maximum likelihood theory states that the most rational choice is to pick the parameter estimate that makes the reality you actually observed as probable as possible.
Let's use a simple analogy. Suppose I'm flipping a coin, and out of 20 flips, I get exactly 10 heads. Now, I don't know for absolute certain if the coin is perfectly weighted, but I need to estimate its true probability of landing on heads.
Well, if you hypothesize that the coin's true probability is 0.5, a perfect 50-50 chance, that specific parameter choice makes the outcome of 10 heads in 20 tosses more likely to occur than any other possible parameter choice. If you wildly guessed the coin's true probability was 0.9, getting a balanced 10 heads and 10 tails would be incredibly unlikely. Therefore, 0.5 is your maximum likelihood estimator. It is the mathematical theory most consonant with your observed reality.
That makes intuitive sense. You fit the theory to the facts. But just because an estimator is the most likely, based on one small sample, doesn't guarantee it is a good estimator of the overarching truth.
You've hit on a critical point there. The estimator itself is a random variable because it's calculated from random data. If you ran your 20 coin flips again, you might get 11 heads and your estimate would change.
Right.
Therefore, statisticians evaluate the quality of an estimator based on its mathematical behavior over the long run. We look for three main properties. Is it unbiased? Is it consistent? And is it efficient?
Break those down for me. Unbiased seems straightforward.
An estimator is unbiased if, across infinite replications of the experiment, the average of all your estimates perfectly equals the true hidden parameter. It doesn't systematically overpredict or underpredict the truth.
It's like stepping on a slightly cheap bathroom scale. Every time you step on it, it fluctuates by half a pound in either direction. But if you step on it 1,000 times and average the numbers, it gives you your exact true weight. It has variance, but it isn't fundamentally biased.
A perfect analogy. The second property is consistency. This concerns how the estimator behaves as you feed it more information. Imagine calculating your estimate with a sample size of 10, then 100, then 10,000.
Okay.
An estimator is consistent if, as the sample size approaches infinity, the estimate zeroes in and converges exactly upon the true parameter. More data forces it closer to the truth.
And efficiency.
Efficiency is a measure of precision. An estimator is efficient if it's unbiased, and its variance, its spread or wobble, is as small as it can mathematically possibly be compared to any other unbiased estimator. We want the tightest possible clustering of our guesses around the true value.
But even if an estimator is perfectly unbiased, consistent, and highly efficient, it produces a single point estimate. And the chances of that single point being exactly microscopically correct in any single trial are essentially zero, which is why researchers provide an interval to give themselves some wiggle room.
Which brings us to one of the most dangerous and widespread statistical traps in all of medical literature: confidence interval estimation.
This is everywhere. You cannot read an abstract without seeing a 95% confidence interval. The new atypical antipsychotic reduced PAN-SS scores by 5 points with a 95% confidence interval of 3 to 7. So let's put this to the test. Let's do a real-time clinical reasoning exercise.
Let's do it.
If I am reading that paper, what is the correct interpretation of that specific calculated interval of 3 to 7? Because the common intuition is that there's a 95% chance that the true effect of the drug lies somewhere between 3 and 7.
And that common intuition is emphatically mathematically wrong.
Wait, really?
Yes. In the strict frequentist paradigm, the true parameter, the actual biological effect of that drug, is a fixed reality in the universe. It is not a random variable. It is a single unknown number. And once you have collected your data and calculated your interval of 3 to 7, that interval is also a fixed set of numbers.
Right.
So you have a fixed truth and a fixed interval. Therefore, the true parameter is either sitting inside that interval or it is not.
The probability is binary. It's either 100% or 0%.
Exactly. It is not 95%. The 95% refers entirely to the reliability of the estimation procedure over the long run, before the data is collected. If you ran that exact clinical trial 100 times and generated 100 different confidence intervals from 100 different samples, 95 of those intervals would successfully trap the true parameter.
Okay.
But once you have a single specific interval lying on the page in front of you, you do not know if you're looking at one of the 95 winners or one of the 5 losers.
I've always thought of it like a game of horseshoes. Let's say I am a master horseshoe thrower. My throwing technique, my procedure, has a 95% success rate of landing a ringer. Before I throw, I have a 95% chance of success.
Right.
But once the horseshoe has left my hand, flown through the air, and is lying in the dirt, the probability changes fundamentally. It is either wrapped around the metal stake or it isn't. If I wildly miscalculate and the horseshoe lands 10 feet away in the bushes, I don't point at that specific horseshoe and say, well, statistically, it has a 95% chance of being a ringer.
That is a phenomenal way to visualize it. The confidence level belongs to the thrower, the statistical method, not to the horseshoe resting in the dirt. When you read a paper and they report a 95% confidence interval of 0.3 to 0.7, you are looking at a horseshoe in the dirt. You're relying on the rigorous technique of the authors, hoping it is a ringer, but the specific numbers themselves do not possess a 95% probability of containing the truth.
That distinction alone changes how you read evidence. Okay, so we have our estimators, we have our targets. But usually in clinical trials, we aren't just estimating. We are forced to make a binary decision. The regulators demand a yes or no. Does the drug work better than placebo, or doesn't it? We are forcing the continuous gray world of biology into a discrete black and white choice.
This moves us into hypothesis testing. If parameter estimation is about finding a target, hypothesis testing is about setting up a structure to falsify a claim. We start by constructing the straw man we intend to knock down, the null hypothesis.
Denoted as H0.
Yes. Formally, a statistical hypothesis makes a statement about the possible values of the parameters. In a standard 2-arm clinical trial, we have the true mean effect of the drug, parameter phi1, and the true mean effect of the placebo, parameter phi2.
Right.
The null hypothesis posits that the mathematical difference between these two parameters is exactly 0. There is no difference. The drug is effectively an expensive placebo.
And the alternative hypothesis, usually denoted as H1, is what the pharmaceutical company is actually hoping to prove. It could be two-sided, meaning the drug could be vastly better or vastly worse than placebo, or one-sided, strictly looking for superiority. But why do we frame it this backwards way? Why not just directly test the hypothesis that the drug works? Why the convoluted focus on proving that the drug doesn't not work?
It traces back to the philosophy of science, largely influenced by Karl Popper's concept of falsification. You cannot conclusively prove a universal positive, but you can definitively falsify a claim.
I see.
More practically, in medical statistics, it is about the asymmetry of scientific caution. The null hypothesis is deliberately chosen to be the scenario whose false rejection would result in the most serious structural error.
Primum non miscere. First, do no harm. If we declare a useless, potentially toxic drug to be highly effective, we expose millions of patients to side effects and financial drain for absolutely no clinical benefit.
Therefore, the entire statistical framework is aggressively rigged to protect against false positives.
Yeah.
Even if the null hypothesis is perfectly true, the drug is literal, water random chance, dictates that occasionally the patients in the drug group will just happen to have a fantastic week, and our test statistic will soar into the extreme rejection region.
Right.
If we reject a true null hypothesis, we commit a type I error, a false positive. We denote the probability of making this error with the Greek letter alpha, and we conventionally set a hard ceiling for it at 0.05. We are telling the universe we are only willing to accept a 5% chance of a false positive to do business.
But rigging the system against false positives creates a vulnerability on the other side.
It creates the risk of a type 2 error, a false negative. This happens when the drug actually works beautifully. The null hypothesis is completely false. But due to a small sample size or excessive noise in the measurement, our test statistic fails to reach the critical threshold. We fail to reject the false null. We denote this error probability with beta.
Which naturally leads to the concept of statistical power.
Power is mathematically defined as 1 minus beta. It represents the ability of your experimental design to successfully detect a true effect and reject a false null hypothesis. It is your study's diagnostic sensitivity.
Okay.
Power depends on 3 intersecting factors: the true biological effect size of the drug, the variance or noise in your patient data, and your total sample size. A well-designed trial calculates the required sample size in advance to ensure the power to detect a clinically meaningful difference is at least 80% or higher.
Let's tie this all together into the most worshipped and simultaneously most misunderstood metric in all of science, the p-value. You open any psychiatric journal and you will see it bolded. Sometimes, tragically, authors only report p-values without any estimates of the actual clinical effect. I want to throw another clinical reasoning scenario at you to decode this.
Okay.
Let's say a massive clinical trial shows a highly significant p-value, less than 0.001, for a new antidepressant over placebo. What does that p-value formally represent? Because the overwhelming temptation is to say there is a 99.9% chance the drug works.
And that temptation is the source of endless bad science. Let's define it with excruciating clarity. The p-value assumes from the very beginning that the null hypothesis is completely 100% true. It assumes the drug does absolutely nothing.
Okay, starting from zero.
Yes. The p-value is the probability of obtaining a test statistic as extreme, or even more extreme, than the one you actually calculated from your data, operating under that strict assumption of a true null.
Let me rephrase that to make sure it sticks. Assuming the drug is nothing but a sugar pill, the p-value is the probability of seeing patient outcomes this vastly different just by sheer dumb luck.
Precisely. It is a measure of how incompatible your observed data is with the null hypothesis. It asks a question about the data, not about the hypothesis. If your p-value is 0.001, it means that if the drug were truly useless, you would only expect to see data this skewed in 1 out of 1,000 identical trials. Because that scenario is so incredibly rare, the math compels us to reject the assumption that the drug is useless.
But the crucial caveat, and this answers the second part of the scenario, is that a tiny p-value does not mean the drug is a miracle cure. It does not prove a massive clinical effect.
It absolutely does not.
Yeah.
Statistical significance is completely divorced from clinical significance. If you have an enormous sample size, say 20,000 patients, you have tremendous statistical power. You can detect a microscopic, trivial difference like a 0.2-point improvement on a 60-point depression scale and generate a highly statistically significant p-value.
Right.
The mathematics is screaming, I am certain these two groups are not mathematically identical. But as a clinician, you look at a 0.2-point improvement and realize it means absolutely nothing to the patient's quality of life.
And conversely, a large p-value, say 0.25, doesn't prove the drugs are equal. It just means your study might have been too small, lacking the statistical power to perceive a reality that is actually there.
Which is why relying solely on p-values without looking at confidence intervals and raw effect sizes is, quite frankly, clinical malpractice.
This all works reasonably well if you're asking one simple binary question, drug A versus placebo. But modern psychiatric research has evolved past single questions. We're testing multiple doses, analyzing dozens of secondary endpoints. We have entered the era of multiplicity.
And multiplicity breaks the traditional rules. This introduces the concept of the family-wise error rate, or FWER.
Let's use a trial design example. Psychiatric trials are astronomically expensive, so researchers try to be efficient. Instead of running 3 separate trials, they design one large trial, testing 3 different doses of a new antipsychotic low, medium, and high against a single placebo group.
A very common and financially sound design. You have 3 specific questions. High versus placebo, medium versus placebo, low versus placebo. These form a family of hypotheses. But here's the statistical trap. If you test each of those 3 hypotheses at the standard alpha level of 0.05, the overall probability of making at least one type I error, at least one false positive across the entire family, inflates dramatically. It's no longer 5%. The maths compounds.
It's like taking multiple shots on goal. Even if the goalie is world-class and stops 95% of shots, if you kick enough balls at the net, eventually one is going to slip through purely by chance.
So statisticians require us to control the FWR. We have to mathematically adjust our thresholds. The most famous and perhaps infamous approach is the Bonferroni method, based on Boole's inequality. It is incredibly simple. You take your desired overall alpha, usually 0.05, and simply divide it by the number of statistical tests you're running.
So for our 3-dose trial, 0.05 divided by 3 is roughly 0.016. To declare any individual dose effective, its specific p-value must be lower than 0.016. It guarantees the overall error rate stays at 5%.
Yes.
But looking at that as a clinician, that feels like a massive penalty. By demanding such a tiny p-value, you're draining the statistical power from your study. You are dramatically increasing the risk of a type 2 error, failing to recognize a dose that actually works. Bonferroni seems too blunt. It punishes you for being thorough.
It is widely considered overly conservative. which is why more nuanced alternatives exist. For example, in your specific scenario where you're comparing multiple active doses to one single shared control group, Dunnett's test is far superior.
How so?
It relies on a specific multivariate distribution that mathematically accounts for the correlation caused by sharing the placebo group. It allows for a more accurate, slightly less punishing adjustment than Bonferroni, while still perfectly controlling the family error rate.
But even Dunnett's test hits a wall when we leave the traditional clinical trial and enter the modern neuroimaging suite. How do we handle massive, high-dimensional data sets? Let me throw another scenario at you. Imagine we're running an fMRI study. We scan a patient's brain, and the image is divided into tens of thousands of tiny 3D pixels called voxels. We are essentially running 50,000 simultaneous hypothesis tests, asking, is this voxel active, for every single one? If we use Bonferroni, we divide 0.05 by 50,000. Our required p-value becomes 0.000001. We would suffer a massive loss of statistical power. We would never find anything. The brain would look statistically dead.
It would completely paralyze research. Attempting to control the family-wise error rate in massive datasets is a fool's errand. This necessitates an entirely different paradigm, the false discovery rate, or FDR.
Before you define the maths, we have to mention the greatest cautionary tale of neuroimaging, the dead salmon study.
Craig Bennett's masterpiece.
It perfectly illustrates why we need these corrections. Researchers bought a dead Atlantic salmon at a local market, put it in an fMRI machine, and showed the dead fish photographs of human beings in social situations.
Yes, a dead fish.
They ran the standard statistical tests without correcting for the thousands of voxels. And due to random noise in the machine, several voxels in the dead salmon's brain showed statistically significant activation when viewing the human photos, a false positive generated purely by the sheer volume of tests.
It is the ultimate proof that multiplicity without correction creates hallucinations in the data. But, as you noted, Bonferroni is too harsh. So FDR offers a compromise. Instead of strictly controlling the probability of making even one single false positive across the entire 50,000 tests, FDR controls the expected proportion of false positives among the specific hypotheses you ultimately decide to reject.
Let's make that concrete. Say I use an FDR procedure in a massive genomic study, and the maths tells me it has identified 100 genes significantly associated with schizophrenia operating at an FDR of a 0.20.
With an FDR set at 0.20, you're making a calculated compromise. You're accepting that 20% of your discoveries are likely rubbish. So of those 100 genes you declared significant, you expect that about 20 are false positives, just random noise. But 80 of them are true, genuine biological signals.
That is a profoundly pragmatic way to handle data. You accept that you'll catch some seaweed in your net, but it ensures you don't use a net with holes so small that you fail to catch any fish at all. You regain the power to make discoveries.
It's a trade-off of certainty for utility. And speaking of paradigm shifts, this naturally leads us into the deepest philosophical divide in statistics, the Bayesian approach.
Bayesian statistics feels like the dark matter of the medical literature. It's slowly taking over. You hear whispers about it in methodology sections, but it feels fundamentally alien to how most of us were trained.
It feels alien because it flips the entire foundation of frequentism upside down. Remember our earlier definition. Frequentists believe the true parameters of the universe are fixed, unknown numbers, and the data we collect is random and fluctuating.
Right. The horseshoe stake in the ground doesn't move. It's my throws that are random.
Bayesians look at the same universe and say the exact opposite. Once you've conducted the experiment and observed the data is fixed. It is a historical reality. It happened. Instead, Bayesians treat the unknown parameters as random distributions.
Okay.
Bayesian inference takes your prior beliefs or prior evidence about a parameter and uses the newly observed data to mathematically update and modify those beliefs.
This revolves around Bayes' theorem. Let's break down the actual equation because it reveals how the logic flows.
The equation states that the posterior distribution, your newly updated belief, is proportional to the likelihood multiplied by the prior, divided by the probability of the data.
The likelihood part makes sense based on our earlier discussion. It's Fisher's concept.
Mm-hmm.
What is the probability of seeing this specific data given a certain parameter? It's the prior that triggers alarm bells for a lot of empirically minded scientists.
Yes, the subjective prior.
If I have a new scenario, say, asking how the Bayesian interpretation fundamentally differs from the frequentist p-value, I get hung up on the subjectivity. Doesn't introducing a subjective prior belief into a mathematical equation completely ruin the objective purity of science? If I am a pharmaceutical company with a financial incentive, Can't I just use a highly optimistic prior to ensure my drug looks fantastic in the final posterior analysis?
That is the classic historical critique of Bayes. What price is paid for introducing subjectivity? But the Bayesian defense is quite potent. They argue that science is already deeply subjective. Researchers use their intuition, their reading of prior literature, and their subjective judgment to decide which experiments to run, which hypotheses to test, and how to interpret ambiguous results.
I see.
Bayes' theorem doesn't invent subjectivity. It forces it out of the shadows. It formalizes it mathematically so it can be transparently scrutinized by peer reviewers.
So the argument is essentially, we all have priors, Bayesians just have the courage to put them in the equation.
Yes. And practically speaking, there are safeguards. If you want to maintain maximum objectivity, you can use non-informative priors, which mathematically state that all parameter values are equally likely before the data arrives. It lets the data speak entirely for itself.
Right.
Or, even better, you can perform rigorous sensitivity analyses. You test the new data against a wildly optimistic prior, a completely neutral prior, and a deeply pessimistic prior. If your final posterior conclusion remains effectively the same, regardless of the prior you fed into the equation, you have discovered an incredibly robust truth.
And the output of a Bayesian analysis is fundamentally different from a frequentist one.
Radically different. Instead of a single-point estimate and a confusing confidence interval, the result is an entire probability curve, the posterior distribution. And here is the true magic, the answer to your earlier scenario. In the Bayesian framework, the p-value actually is what every clinician mistakenly thinks the frequentist p-value is.
Wait,
Yes. A Bayesian analysis can directly calculate the probability that the null hypothesis is true, given the data you just observed. Bayes asks a direct question about the hypothesis. Frequentism asks a convoluted question about the data.
it actually gives you the answer you wanted when you designed the study. That alone explains why it is gaining so much traction. But regardless of whether you process your data using frequentist or Bayesian maths, your conclusions are only as valid as the data you feed into the machine, which moves us to the actual generation of data. We must explore experimental design because in psychiatry, our ultimate goal isn't just observation, it is proving causality.
We don't just want to know that people who happen to take an antidepressant are less depressed. We want to prove that the molecule caused the relief. And defining causality in a mathematically rigorous way is surprisingly difficult. The dominant framework we use was formalized by Donald B. Rubin. It is known as the potential outcomes framework, or more colloquially, the counterfactual model.
This is the part of experimental design that always feels a bit like a science fiction multiverse.
It requires visualizing alternative realities. Suppose you give a patient a new psychiatric drug, and 6 weeks later, their symptoms have resolved. Did the drug cause the resolution? To know for absolute mathematical certainty, you would have to freeze time, rewind the universe to the exact moment of prescribing, and give that exact same patient a placebo instead. You need to compare the outcome under treatment against the counterfactual outcome under placebo.
What would have happened if they took the blue pill instead of the red pill?
Exactly. If the outcome under treatment is measurably better than the outcome under placebo for that specific individual, you have definitively proven individual causality. But, barring the invention of time travel, we suffer from the fundamental problem of causal inference. An individual patient only ever receives one treatment at a time. The alternative outcome is forever counterfactual. It is unobservable.
So if we can't prove causality in a single human being, how do we ever prove a drug works?
We are forced to move from the individual to the population. We rely on statistical averages. We want to prove that the average expected outcome for a group taking the treatment is better than the average expected outcome for a group taking the placebo. But here's the fatal flaw if we aren't careful. We are observing the treatment outcome and the people who actually took the drug, and the placebo outcome in an entirely different group of people.
Which introduces massive potential for bias. What if the people who actively sought out the new drug were generally healthier, or had better social support, or were simply more motivated to recover than the people who ended up taking the placebo?
Then your causal inference collapses. You're measuring the power of motivation, or the benefit of wealth, not the efficacy of the medication. To mathematically conclude causality, you require a mechanism that makes the assignment of the treatment completely independent of the patient's potential outcomes.
Enter randomization, the absolute gold standard of clinical research.
Randomization is the great statistical equalizer. If a patient is assigned to the drug or the placebo strictly by the flip of a coin or a random number generator, then the treatment assignment mechanism is utterly blind. It is independent of their baseline symptom severity, their genetics, their socioeconomic status, their hidden traumas, everything.
It scrubs away the biases.
Importantly, it controls for unknown biases. If you try to manually match patients, say, pairing up two 30-year-old men with severe OCD and giving one the drug and one the placebo, you're only controlling for the variables you are smart enough to measure. Randomization magically balances the variables you didn't even know existed. It validates the calculation of experimental error and guarantees the mathematical independence of the observations.
I do want to note a clinical reality here, though. Randomization gives you incredible internal validity. It proves causality for the people in your trial. But it doesn't solve selection bias. If your trial has draconian inclusion criteria, excluding anyone with a comorbidity or anyone taking other medications, your results might be perfectly true for that pristine sample, but utterly useless when applied to the complex, messy patients sitting in your real-world waiting room.
That is the eternal struggle of generalizability. But staying within the trial, there's an integration point here about how we analyze randomized data. Sometimes we're in the trial, flip the coins, crunch the averages of the whole group, and see zero difference between drug and placebo. The trial is declared a failure. But there is a more nuanced way to look at this, isn't there?
Yes, the likely responder method. Psychiatry is notorious for wildly heterogeneous clinical presentations. Major depressive disorder is probably dozens of different biological phenotypes lived under one umbrella. If you average everyone together, the massive statistical noise generated by the non-responders can completely drown out the genuine signal of the specific subpopulation who actually benefited from the drug.
There is a classic example of this in the literature regarding the use of gabapentin for alcohol use disorder.
It's a perfect case study. In the initial standard analysis of the whole randomized sample, there was no significant treatment difference between gabapentin and placebo. It looked like a total failure. But researchers like Eugene Laska and Carol Siegel pioneered a reanalysis using the likely responder approach.
They didn't just throw the data away.
Exactly. First, they used baseline characteristics to mathematically identify a subset of patients whose profiles made them theoretically likely to respond.
They isolated a specific phenotypic profile hidden within the larger group. Then they performed a targeted test of treatment differences solely on patients within that specific subgroup, carefully matching them on baseline features. And suddenly, operating within that subset, a highly significant causal effect emerged.
Wow.
This approach to causal analysis within a potential outcome framework is the vanguard of precision medicine. It stops us from discarding a potentially life-saving molecule just because the average of the whole population diluted its effect.
But let me pose another clinical dilemma. What happens when we can't randomize? In psychiatry, we study trauma, abuse, environmental exposures. We cannot ethically randomize a group of children to experience severe neglect versus a nurturing environment to study the causal effects on brain development.
No, we absolutely cannot. We are forced to rely on observational data. And drawing robust causal inferences from messy, naturalistic data requires profound statistical creativity. We essentially need to build a pseudo-randomized trial hidden within the observational data. We accomplish this through a technique called propensity scores.
I find this concept fascinating. Walk us through how we use maths to find a patient's statistical doppelganger.
Suppose you have a massive national registry of patients who either received a cutting-edge, expensive therapy, or standard clinical care. It wasn't randomized. Individual doctors simply chose who got what based on clinical hunches or insurance coverage. To isolate the real effect of the new therapy, you first feed all the data into a logistic regression model. You include every single patient covariate you have: exact age, baseline severity, gender, past treatment failures, socioeconomic status.
You build a comprehensive mathematical profile of each person.
And the model outputs a single defining number for each patient, their propensity score. This score, ranging from 0 to 1, is the estimated probability that this specific patient would have been assigned to the new therapy, based entirely on their background characteristics, regardless of what they actually received.
So even if a patient named John ultimately received the standard care, his severe symptoms and past history might dictate that he had an 85% propensity score and 85% likelihood of getting the new therapy.
Precisely the logic. Once everyone has a score, we divide the entire patient population into strata, typically quintiles, based purely on those scores. Within any single stratum, all the individuals have approximately the same estimated likelihood of having been assigned to the new treatment.
So if I look at stratum 5, every single patient in that bucket has roughly an 80 to 90% chance of getting the new therapy based on their clinical traits.
Yes. And because their traits are mathematically balanced, the multivariate distribution of their covariates is statistically indistinguishable within that stratum. They look like identical clones to the algorithm. But here is the critical part. Within that exact same stratum, some people actually received the new therapy, and some people actually received the standard care.
It's brilliant. It mimics randomization. Because if two patients are statistically identical in every measured way, but they receive different treatments, it's as if an invisible biased coin was flipped to decide their fate. You've isolated the treatment variable from the confounders.
It is a masterful piece of statistical rescue work. You estimate the treatment effects separately within each of the propensity score strata. If the results show a consistent effect across the strata, you can combine them for an overall highly robust estimate of the causal effect size, even without a true randomized trial.
This brings us into the final conceptual stretch, advanced clinical reasoning. We've talked extensively about testing pristine, perfect data, but anyone who has ever run a clinical trial knows the data is never pristine. Real-world clinical data is messy, it's incomplete, and it frequently breaks our neat linear models.
To manage that reality, we employ a variety of advanced analytic techniques. We have briefly mentioned regressions. Linear regression uses ordinary least squares, or OLS, which mathematically aims to minimize the sum of the squared errors, the distances between the observed data points and the predicted model line. We use complex contingency tables, calculating the Cochran-Mantel-Hansel statistic to test for conditional independence across complex variables, like ensuring the specific hospital site didn't skew the results of a multi-center trial.
But beyond just crunching the numbers differently, we can change the architecture of the study itself. Let's talk about crossover designs. This is where the patient serves as their own control group. You give them drug A for 6 weeks, wash them out, and then switch them to drug B for 6 weeks.
Often referred to as an BA design. Half the trial gets sequence A, then B, the other half gets B, then A. The statistical advantage of this architecture is enormous. Because you're comparing the patient's reaction against their own baseline, you completely eliminate between subject variation from the statistical error term. You need a fraction of the sample size to achieve the exact same statistical power as a parallel group trial.
It sounds incredibly efficient. Why aren't all psychiatric trials crossover designs?
Because of the unique biological reality of psychiatry, crossover designs are deeply vulnerable to carryover or residual effects.
The ghost of the first treatment haunting the second phase.
Exactly. Does the biological effect of drug A linger and systematically contaminate the patient's response to drug D in the second period? If you are running a trial for a mild analgesic treating a headache, a crossover works beautifully. The headache resolves, the drug clears, and you start fresh the next day.
But in psychopharmacology?
In psychopharmacology, drugs fundamentally alter receptor densities over weeks. Psychological therapies like CBT teach cognitive skills that cannot be unlearned. The regulators are notoriously and rightfully skeptical of simple two-period crossover trials in psychiatry for this exact reason. If a carryover effect is present, the simple BA design is essentially ruined.
Is there a mathematical fix for carryover?
We can attempt to fix it by adding more periods to the design. Moving to an BAA design or extending to a 3-period sequence allows statisticians to mathematically isolate and estimate the carryover effect, effectively separating it from the true biological treatment effect. It restores the statistical power of the crossover, but the obvious trade-off is that it drastically increases the time burden on the patient.
And when you increase the burden on a psychiatric patient, you inevitably trigger our next major clinical hurdle: missing data.
Dropouts are the bane of every clinical researcher's existence.
Yeah.
Patients move away, they get exhausted by the endless rating scales, or they experience adverse events and simply stop showing up. You're left with an incomplete data matrix. And how you mathematically handle the holes in your spreadsheet can entirely alter the final conclusions of your trial.
It all comes down to the missingness mechanism, why the data is missing in the first place.
Statisticians Roderick Little and Donald Rubin formally defined the 3 key mechanisms. The simplest and most forgiving scenario is M playing R. Missing completely, at random.
I always explain this with the coin flip analogy. If a patient's data is missing simply because a random event occurred, say, the phlebotomist accidentally dropped their blood vial on the floor, or their car broke down on the way to the clinic, the data is MPR. The missingness has absolutely nothing to do with the patient's underlying health status or their biological reaction to the drug.
And from a statistical standpoint, MCR is a relief. If the data is truly missing completely at random, the remaining data that you do possess still constitutes a perfectly random, unbiased subsample of your original trial population. You will inevitably lose some statistical power because your overall sample size has shrunk, but your final conclusions won't be structurally biased.
But let's look at a much more common psychiatric reality. What if the patient dropped out because the side effects of the experimental antipsychotic were intolerable? Or what if the antidepressant was completely failing and they became so profoundly depressed they couldn't physically get out of bed to attend the assessment?
That scenario is decidedly not missing completely at random. That falls under a non-ignorable missing data mechanism. The fact that the data is missing is directly caused by the unobserved data itself, the patient's severe depression or intense side effects. If a researcher simply ignores those dropouts, deletes their rows, and only analyses the highly motivated completers who happily stayed in the trial to the bitter end, the results will look artificially fantastic.
You've hidden all the failures.
You've constructed a fatally flawed analysis. To handle non-ignorable missing data, statisticians must deploy highly complex modeling to try and infer the missing values from the trajectory of the observed data. But it is an incredibly fraught process built on fragile assumptions.
Which perfectly sets up our final and arguably most vital clinical distinction for anyone interpreting medical literature: the profound difference between efficacy and effectiveness. Let's frame this as our final clinical scenario. If a patient drops out because the drug made them nauseous, where do their numbers go in the final analysis? How you answer that depends entirely on what question the trial is trying to answer.
It is the most important concept for a clinician reading a paper. Efficacy studies, the classic, gold standard double-blind RCTs, are conducted in pristine, highly controlled, laboratory-like environments. They feature draconian eligibility criteria, intensely trained staff, and constant patient monitoring. Efficacy studies are designed to answer one very specific, narrow biological question: can this drug work under absolutely ideal, perfect biological conditions?
It tests the maximum theoretical potential of the molecule.
Yes, but effectiveness studies ask a fundamentally different question. Does this drug actually work in the messy, chaotic real world? Efficacy trials deliberately exclude the very patients most likely to be sitting in your waiting room. Patients with multiple psychiatric comorbidities, patients who struggle with substance use, patients who are chronically non-compliant with medication. Effectiveness studies, by contrast, take all comers in naturalistic, real-world clinical settings.
And because the real world is messy, the way we analyze effectiveness data requires a completely different approach. We use the intent-to-treat analysis.
The ITT principle. In a strict intent-to-treat analysis, once a patient is randomized into a treatment arm, their data is analyzed as part of that arm forever, no exceptions, even if they never swallowed a single pill, even if they dropped out of the trial on day 2. Even if they fundamentally broke the rules and secretly crossed over to start taking the other group's medication.
That concept often sounds insane to medical students at first glance. Why on earth would you include a patient's outcomes in the drug A data pool if you know for an absolute verifiable fact they didn't take drug A? Doesn't that dilute the data?
It dilutes the biological signal, yes. But you are no longer testing the pure biological action of the molecule. In an ITT analysis, you're testing the real-world effectiveness of the policy of prescribing the drug. Think about it clinically. In the real world, if you write a prescription for a highly effective but horrible-tasting medication, some patients won't fill it at the pharmacy, some will take it sporadically, and some will quit abruptly due to the taste. An intent-to-treat analysis evaluates the clinical effectiveness of your decision to treat, incorporating all the blemishes, non-compliance, and human error that inevitably follow that decision.
It brutally protects against the massive selection bias of only counting the highly motivated, biologically robust, perfect patients. It tells you what will actually happen when you unleash this drug into the general population.
It is the ultimate mathematical bridge between abstract statistical theory and the gritty reality of clinical practice.
This has been a monumental journey. We've moved from the philosophical definitions of probability through the deceptive traps of confidence intervals and p-values, navigated the complexities of multiplicity and Bayesian priors, and landed right back in the messy reality of the clinic with propensity scores and intent-to-treat analyses. Now, to make sure these concepts have actually anchored themselves in your mind, we're going to transition into the testing phase. I'm going to ask a few single best answer questions based on what we've covered. I'll read the question, give you a brief second to think about the answer, and then we'll break it down. Ready?
Let's test the architecture.
Question 1. In the frequentist paradigm, what is the correct interpretation of a 95% confidence interval once the data is collected and the interval is calculated? Take a second to think about it.
The answer is that the true parameter is either within the interval or it is not. The probability is exactly 1 or 0. The 95% refers to the reliability of the estimation procedure over infinite replications, not the specific calculated interval lying in front of you.
Right, the horseshoe is either on the stake or it isn't.
Mm.
Question 2. A clinical trial shows a highly significant p-value, say, PE, is less than 0.001 for a new antidepressant over placebo. What does this p-value formally represent? Think carefully about the assumption it makes.
It formally represents the probability of observing a test statistic as extreme or more extreme than the one calculated, assuming the null hypothesis that there is no difference between treatments is completely true. It does not represent the probability the null is false, nor does it prove clinical relevance.
Spot on. Question 3. In a neuroimaging study analyzing 50,000 voxels, which statistical method is most appropriate to manage the multiplicity problem without suffering a massive loss of statistical power?
That would be the false discovery rate, or FDR. Unlike the Bonferroni correction, which attempts to control the family-wise error rate and is overly conservative, FDR controls the expected proportion of false positives among the rejected hypotheses, making it much more suitable for massive datasets.
Question 4. How does the Bayesian interpretation of a p-value fundamentally differ from the frequentist interpretation?
In a Bayesian framework, the resulting probability incorporates prior beliefs and actually represents the probability that the null hypothesis is true given the observed data, whereas the frequentist p-value is the probability of the data given a true null.
It answers the question you actually wanted to ask. Question 5. When analyzing observational data where true randomization is impossible, what technique mimics randomization by matching subjects based on their estimated probability of receiving the treatment given their covariates?
Propensity score matching. It attempts to isolate the causal effect by balancing confounding variables across groups, creating statistical clones based on their likelihood of treatment.
And the final question, question 6. In a clinical trial analyzing real-world outcomes, what type of analysis keeps all subjects in their originally assigned groups, regardless of whether they actually complied with or completed the treatment?
Intent-to-treat analysis. It evaluates the effectiveness of the policy of prescribing the treatment in real-world, naturalistic conditions, blemishes and all.
Brilliant. If you struggled with any of those, I highly recommend directing yourself back to the chapter in Kaplan and Sedok to review the core mechanics.
It is a lot of architecture to absorb, but it is the only way to independently verify the truth of what we practice.
And I want to leave you, the listener, with a final provocative thought to mull over as you read your next journal article. We talked earlier about the likely responder method finding the signal hidden in the noise of a failed trial. Think deeply about the implications of that mechanism. If our statistical tools dictate what we officially consider true in psychiatry, how many truly effective treatments, how many life-changing molecules have we permanently discarded over the decades simply because our rigid trial designs averaged out the likely responders into a massive, noisy sea of non-responders? The maths is not neutral. It shapes our reality. Consider how the underlying architecture of your next study might completely change the truth you uncover.
A vital reminder that methodology is destiny in clinical research.
Here are the details of this episode. PSYCH 057, Statistics and Experimental Design. Byline. Truth in psychiatry is not obvious. It must be carefully designed, tested, and interpreted.